All right, so today we're just going to finish up with DFS and move on to BFS, breadth first search. So we left the discussion off on Wednesday talking about what the complexity of DFS is. And so clearly the input is going to be the graph. And the input size is, you can either think of it in terms of the number of vertices, n, or you can think of it in terms of the number of edges, m. That's reasonable too, but you have to understand that they're polynomially related, right? If I have a complete graph on n vertices, then there are n choose 2, which is n squared edges. So the number of edges is always going to be bounded by n squared. It really doesn't matter. When you you come out with your final analysis, it's going to be n, m, or some polynomial relationship between them. So you can think of it in either terms, and you should be good to go. Right? What was the elementary operation, though? Well, we identified several things, right? We could say a vertex examination or traversal. Anytime you step on a vertex and you discover that vertex, or you look at a vertex and you see that it's been colored gray or that it's been colored black so that you don't want to go to it again, right? A vertex examination or a traversal, or an edge examination or traversal. And for every edge, you can look at it from one of two ways. If an edge is going to connect two vertices A, B, so you first see it from A's perspective, you second see it from B's perspective, you're only ever going to examine an edge exactly twice, or at most twice. Or finally, what you actually want to use as your elementary operation, the processing of an actual node, right? And no matter what, I mean, if you look at the processing of an actual node, it's going to be then order n, right? Each node is processed exactly once. So it's going to end up being order n. And that's the real DFS, right? You could look at it from the perspective of the edges. You could look at it from the perspective of the vertices. But just like a sorting algorithm, those things are necessary for the control structure of the algorithm. What you're really doing is you're doing some sort of a data processing. And that's probably going to be the most expensive thing. So pay attention to that, and it then becomes a simple linear algorithm, right? You do everything exactly once, okay? We've already talked about a few of the artifacts that can come out of DFS, and we'll return to the applications of DFS later. But let's take a look at the other companion strategy, breadth first search. So breadth first search explores closely first, right? It explores the graph, explores the graph by spanning out from a central vertex. That's the way I'm going to put it. Basically, it explores near vertices first before moving out, right? So for example, let's just go ahead and look at the same graph over here. And to make it a little bit more interesting, what I'm going to do is I'm going to start my breadth first search right here at B, all right? So I'm going to start at B, and then I'm going to expand out from there. The way that I do that is I look at the entire neighborhood here, right? I'm looking out at things that are immediately connected to it, right? A, C, D, and G, right? And then I explore all of those things before I move on to the rest of the graph, things that are a distance 2 away. So you'll note here that I'm exploring first everything that is a distance 0 away from my starting vertex, then everything that is a distance 1 away from my starting vertex, then everything that is a distance 2 away from my starting vertex, right? So I'm starting and I'm going out in a radial pattern basically here. And that's what a breadth first search is. And that's how, a lot of searches in real life are done. If you're searching for a missing person, right? This is the last place you saw them. Do you go immediately over here 50 miles away and search in that one location? No. You assume that that they've gone on foot or something like that, and so you go out in a radial pattern here, right? And you search the closest things first, right? So in the order that we're doing this is, of course, we got A, right? Or sorry, we start at B, right? B. Then we explore B's neighborhood here, which is A, C, D, and G. And again, the same criteria as before. You could go in lexicographic order. You could go in reverse lexicographic order. You could go in order of edge weights, whatever. I'm just going to go into lexicographic order here, right? So we explore A, C, D, and G next, right? In that order, okay? So now we need to expand out one level more, right? In other words, we're going to start at A here. So let's consider A next. Oops, undo that. A. We already did, so we did C, we did D, and we did G already, right? So we start from the next vertex, A. And we look at everything in its neighborhood. Well, that includes C, but that's already been explored. That includes B, that's already been explored because that's where we started. And so H and I here are the ones that we would explore next. Oops. H and I. There we go. And those end up being explored and done with. There we go. Now, remember that we've done B, we've done A, and we've explored its neighborhood. Now we look at C. Well, everything in C has been explored already. Everything in C's neighborhood has been explored already, so we end up doing nothing. Right? We move on to D. Where's D? Right there. So it's got several things in its neighborhood. C, B, and G have all been explored already. F and E are next, so we put those into our list of things to explore, and now we're done with G. Now, we've discovered everything at this point. So what's going to happen is we go through the rest of these things, we process them, they get done, and there's the end of our algorithm. Now, why did I write it in a row like this? What kind of data structure does that look like if I drew it like that? A what? A list, okay. And things went in one way, and then they came out the other way. Right? That's a queue. Right? Anytime that we discover something, right? We put it into the queue over here. Anytime we're done with it and we process it, we take it out of the queue. Right? So discovery time, processing time, just like DFS. But instead of a stack, we use a queue. Right? In fact, it's the exact same code. All you have to do, I don't know if you remember or not, but when we did DFS, like pre-order traversal, all you had to do was change your data structure from a stack to a queue, and you had BFS on a tree. Right? If you have a tree here, what does a BFS look like? You start top to bottom, left to right. Right? And each time you are done with a row, you go to the next row, the next row, and the next row. Now take this big line, a big squiggly line, and stretch it out, and there's your queue. Right? If it's A, B, C, D, E, F, G, H, right? All it is A, B, C, D, E, F, G, H. Right? There's your queue. Right? So this suggests that we have very, very simple code for BFS. Right? Here's my, let's go ahead and write it out. BFS of, say, G and V. Right? So the input here is a graph, an undirected graph. Graph G equals V comma E, right? And an initial vertex V, okay? Now, why do I have an initial vertex here? Because you might need to restart your BFS. Remember, I forget what we were doing, where was my example here? There's a disconnected graph. I've got 1, 2, 3 connected components. If I did a BFS on this, right, and I started in one component, here's my BFS, and then I go out to its neighbors right here, right? There's my, but have I explored the entire graph? No. I may need to restart the BFS at another connected component, in which case, I have to restart it. And this is going to be the subroutine that I do that in, right? That if I have to restart it, I call this multiple times. I call it on an initial vertex X. And then in the main, there's another unvisited vertex, And so I'll call it again and again and again, all right, starting at a different vertex, okay? All right, so here's my input. My output will be a breadth first search processing. Now in our BFS, we are going to keep track of all of the same artifacts: discovery time, finishing time or processing time, and then we're also going to color the vertices from white to gray to black in order to indicate whether or not it's been unvisited, visited but not yet processed, and then done processed. Okay, and we're going to keep a counter here. Count will be initialized to 1, just like DFS. Right? And instead of a queue, or instead of a stack, excuse me, we're going to have a queue. A first in, first out data structure. We'll mark our initial vertex here, V, with count. That's its discovery time. We will color V gray, right? Visited, but not yet processed. And then we will enqueue it, q.enqueue. V. Okay. By the way, as an aside here, now that we're playing around with stacks and queues, in Python, are there stacks and queues in Python? Nope. They're just, what did you call it at the very beginning instead of a queue? It's a list, right? And a list you can operate on either end, right? What is it? What are our options with a list? A Python list. There's remove, and that removes it from where? Fine. You can put in the index. So remove 0 removes at the front, and then just remove without 1 removes it at the other end. Append appends it at the end. I think you could do, but also you've got pop, right? And I think you've got push too. Don't you? Maybe not. No, you don't. You just have append and pop, and that operates on this end. So you can treat it like a stack using append and pop.
So pop operates at the end?
At the end, I believe. Yep, doesn't it? Removes, well, okay, you can specify an index there as well, but by default, I think it's going to go on the end.
If you do not specify.
There you go, last item. All right. That's why we say RTM, right? Read the manual. Right. All right, so there's our aside. This is all just initialization right here. Right. Initialization. Okay. Now we need the main loop here. So we've already got one thing in our queue. We're going to continue operating until our queue is completely empty. So while queue is not empty, what I'm going to do is I'm going to grab the thing at the front of the queue, and I'll call it X, q.dequeue. Dequeue, UE, right? Dequeue just means remove something. Now, if you're in an opera, it's not too common that I've seen enqueue and dequeue as named operations on a data structure. It's usually pull and offer, or in the case of Python, it's going to be append, remove, pop, push, whatever, right? So when I say dequeue, I mean when I say dequeue, I mean whatever is next out of the queue, pull it out of the queue. Right? And then for each y in the neighborhood of x, right? If y is white, that is unvisited, right? Then we increment our counter, count plus plus. We mark y gray, and with a discovery time equal to counter. And then finally, I'm going to go ahead and go over to the next line here. Right. We enqueue, q.enqueue y. There we go. Okay. That's the end of the inner for loop. That's the end of the for each loop. And now we're in the while loop continuing here, right? So after we've enqueued all of its unvisited neighbors, right? Note here that we are ignoring anything that is already gray or black. Anything that's already been processed, anything that's already been visited and enqueued, but not processed yet, right? After all that's said and done, we increment our counter again, count, and we finish up with X. We end up processing X, process X, right? Because we dequeued it, we looked at all of its neighbors, and we took care of them, and now we need to actually process this node X here. Process X by mark X black, that is processed and done. And then mark X with a finish time of counter. And that's it. That's the end of the outer while loop there. Right. Now, if you want one that is not broken up because we don't have enough real estate here, there it is in the book. Okay. Again, this section right here, this for each section, right, all the way down here. This is processing the neighborhood of X. Okay. Put stuff in, take stuff out. Smart data structures, that's all you need. Okay. So once again, if we look at that other, at that graph again, let's start somewhere else and simulate this algorithm, right, as we go along here. And I'll go ahead and use blue. Give me a vertex to start at. B? Oh, that's what we did before.
Let's go with B.
D?
B for boy.
Oh, okay. Oh, sorry. B is what we did before. Oh, what did you say before? D?
Initially I said B, but it's the same thing.
Yeah. Okay. Let's start. Let's just start at D. Right. D for dog, right?
Yeah.
Okay. All right. So, what does my queue look like? Come on. There we go. So I've enqueued D, right? And I've discovered it at timestamp 1. Right? It's gray, or in this case, blue, right? Because I don't have nice gray here. So sorry if this is not coming up. It should come up, right? I don't know if are blue and gold or whatever this is, orange, are they color? Am I choosing the correct color for colorblind folks? Can you see it? Okay. All right. Great. Excellent. Right, well, there are several different kinds of colorblindness too, right? All right, so I've discovered D here. And now what I do is I go through its entire neighborhood. So what I'm doing here is the neighborhood of D at this point, right? So I've dequeued D, and this is my current vertex, right? And I look at its neighborhood. I see C, G, B, E, and F. I'll just go ahead and go in lexicographic order. B, C, E, G, F, G, thank you. F and G, there we go. And what I've done along the way here is each one of these things I've colored gray, or in this case blue, that I've visited them. Right? There we go. And the order in which I did it was 2, B, 3, 4, 5, and 6. Right? At which point I am done with D. Oops. And so I color it black. In this case, I'll just use gold. Right? And I'm done with it. That has a processing time of, my counter is up to 7 now, and I'm done with it. Right? And it is out of my queue. So the next thing I do is I dequeue whatever's next here, which is B, right? And I look at its neighborhood, and I see that there's some gray vertices here, some blue vertices that have been visited. That's because they're still in the queue here. But I've also see some vertices that are processed and done, so I don't want to return to those. But I do see a vertex here, A, that is unvisited. And so we visit that. We mark it as timestamp. I'm up to 8 now. Right. There we go. And we're done with B. So we mark it with our next timestamp, B, and then that is now done. Right? Okay, it wants a square there instead. Right? And that's out of the queue. I look at the front of my queue, and what do I see? C. Right? Well, there's nothing in its neighborhood that is unvisited white, so we just go ahead and are done processing it. I don't know why it really... Yeah. I mean, I don't know. Come on. There you go. Right. It's just auto-detecting here. So it's done at 10. And it's out of the queue as well. Same thing's going to happen for E. All right. It's just going to end up being processed with nothing left in its neighborhood to visit. So we're now up to 11. Right. There we go. F is next. And we do see something in its neighborhood, I. So we NQ it, we mark it with the next timestamp, 12. Right? And at that point, we're done with F, so 13. And there we go, oval. And it's out of the queue entirely now as well. G, that comes out of the queue. And we NQH, discovery time of, what am I up to, 14? H, there we go. And at this point, everything has been discovered. So fast forwarding here, what do? Process all the rest in the order that they're in the queue. So that's going to end up being what? GAIH, so 15, 16, 17, and 18, and they all end up being colored black and DQ'd out of the queue. Right? There. At that point, the queue is empty and the algorithm terminates. Yeah.
Do we ever use a timestamp?
You'll note here that all the order of the timestamps is exactly the same because it's a queue, first in, first out, right? That if you were to order them, it would end up being B, C, or sorry, D, B, C, E, F, G, A, H, I, H. And then if you ordered them in finishing time, it'd be the same order, right? So it doesn't give you as much information as, say, DFS does, but it can be useful for some things. But you can use this, you can generate the same artifacts. For example, you can generate a BFS tree out of this. What would it look like? We started at D, right? And then we looked at its entire neighborhood in a particular order. B, C, E, F, and G. There we go. So here's the BFS tree. There. All right, what did we discover from there? Off of B, we have A. Off of C, we had nothing. Off of E, we had F. Right? Off of what? Oh, sorry, you're right. E, F. Off of F was I, right? No. Off of A was I. No. Darn it, what did we do? Darn it. Here, I should have highlighted all the tree edges here. No, what? We started with D, damn it. All right, 1, 2, 3, 4, 5. Then we went from B to A. Then C, no. Then E, no. F to I. There we go. All right. Then off of G was H. There we go. Right. So a very, very shallow tree, which is what we would expect because BFS explores the nearest elements first. What does this tree tell you about with respect to D? On an unweighted graph here. This is the shortest distance path to every other node from D, right? And it gives you that path. How do I get to A? From D in the shortest amount of time, or the shortest path. All you need to go is go to B. Is there any other shortest path to go from D to A? Well, there would have to be an edge there. Right? There might be other alternate paths, but this one is the shortest. These are all the shortest because they're immediately connected, and everything else has a maximum distance of 2 from D. Okay? If I had generated this BFS tree with respect to B instead, I would be generating all shortest paths from B instead. Right? This only works for undirected, unweighted graphs. Right? For other types of graphs, we need more sophisticated algorithms. Right? Okay. So what about these other edges here? For example, I to A. What does that look like? What kind of edge is that? Remember that we've got forward edges, back edges, and tree edges, and then cross edges. What kind is this? Back edges are ones that are going to connect back to an ancestor in the tree. Forward edges are ones that are going to go forward. So because it's undirected, forward, back edges are the same. This one is going to end up being a cross edge, right? Because it connects distant cousins in the tree, right? Not grandfather to son, or father to son, son to grandson, then grandson to grandfather, right? All right, what are some others? What about C and A? C and A? They're not ancestors either, right? That's an uncle, I think, right? Because this is your father, and then that's their brother, and so that's your uncle, right? So that's also a cross edge. What else do we have? C and B? Siblings. Also a cross edge. I'm seeing a pattern here. Could there be a back edge? What if we had D to A? Yeah, that would be a shorter path, and therefore BFS from D would have discovered that immediately. This would have been one level up off of this. Right? So are forward edges or back edges possible? Nope, because it's BFS. Only other cross edges are possible. A and H. A and H. Very distant cousins there. Right? I don't know. F and E. There. Siblings again. And I think I got them all there. Right? So in a BFS tree, you only have tree edges, undirected graph, unweighted graph. You only have tree edges connecting immediate descendants or ancestors, and everything else is going to automatically be a cross edge. Right? If you have a forward edge, that means that you would have had a different BFS enumeration. Right? Okay. So what about all of the other items here? Right? Let's make these observations. Again, in a BFS tree, for undirected graphs, there are no forward edges are possible. Right? Otherwise, they would have been discovered during the BFS traversal. Right? In a directed graph, back edges are possible. Right? You can go back from a descendant to an ancestor, but forward edges are not, for exactly the same reason. Right? You can have a back edge because from up here, you can't traverse that edge downward because it's oriented upwards, right? Both have potential cross edges. Cross edges, right? In a undirected graph, directed graph, cross edges imply ... what? What do these cross edges imply? So here's a tree edge, and then there's a cross edge. What is this right here? A cycle, right? So if you have any cross edges, then you have a cycle. Imply a cycle. Right? BFS may need to be restarted if you have a disconnected graph. And for the same reason, what you can do is you can use BFS, just like we use DFS, to count how many connected components we have. and therefore answer, is it a connected graph or a disconnected graph, right? What about the analysis? Right. Same. Why? Because you only ever process a vertex once. You only ever traverse an edge at most twice, right? If it connects A to B, you look at it once, A, from the perspective of A. You look at it twice from the perspective of B, right? So again, it's going to be the same, order n. That's it. All right? Questions so far on any of this? Otherwise, what you have 1 week from today is here's an input graph, generate a DFS, generate a BFS according to these criteria. Tell me if it's acyclic or not. Tell me if it's a tree or if it's or if it contains a cycle. And one other observation, right? The BFS tree can be used to determine the shortest path from the source, that is the starting vertex, to any other connected vertex, but only for undirected, unweighted graphs. Okay? The BFS tree gives you that for free. So it works, but it only works for a very specific type of graph. Okay? Yeah.
Are the graphs given on the homework all undirected and weighted?
Undirected, weighted. That's what we give. From a practical perspective, it matters, right? When you actually program this stuff. But from a theoretical point of view, it doesn't really matter. Why? Because you've got these things called morphisms, homeomorphisms, homomorphisms, et cetera, where if you've got, like, say, a weighted edge, you can always just replace that with a series of unweighted edges, right? You can replace and then you can contract it as well. You can contract a path down to something else, right? All right. Any questions? No? All right. Then I'll save this digression for later. Let's talk about some other applications. Right? For example, connectivity. Right? Given two vertices in a graph, G equals V comma E. Right? And let me go ahead and label those vertices too, U and V. Right? In V. There we go. Is that all rendering correct? Yep. Good. Determine. Does there exist a path from connecting U and V? So ideas. How could we use DFS? Could we use BFS? Both? Neither? BFS or DFS? Same criteria. How would you do it with BFS?
Map the whole thing and see.
So run it once from, say, U. Say that this is U, right? And run a BFS. And if you ever encounter V, do you need to do the rest of this stuff? Nope. Immediately stop, right? Because you know that you found a path to V, right? And it works for directed graphs as well, right? Perform either starting at U, right? If you ever encounter V, that is you NQ or you push it into your data structure, stop. Answer yes. Right? However, if you have to restart BFS or DFS in order to get to it, to explore it, that means that it's in a completely different connected component. There is no direct path, right? Otherwise, no, right? Pretty simple. Okay. Another application here, cycle detection. We've talked about this before, right? Given a graph G, does there exist a cycle in G. Or, alternatively, if it doesn't contain a cycle, what kind of graph is it? It must be a, what do we call those things? Acyclic graphs? Tree, right? So how could you do this? DFS or BFS, right? If there are no back, forward, or cross edges, right? Then it must be a tree. Right? Another way that you could do this is run DFS, BFS. Right? If you ever encounter a visited vertex that you did not immediately come from, you found a cycle. Visited. Right? Now, why do you have to exclude the one that you immediately came from? Let's come back over here and look at that graph again. Right? If I'm about to perform a DFS from, say, I, right? And so now that's gray. I go to A next. And I'm looking at the neighborhood of A. I see a bunch of unvisited vertices, C, B, and H. But I also see this vertex over here that's gray. Right? Does that mean that there's a cycle here necessarily? Nope, not necessarily, right? I just came from there, right? So I need to make sure that I'm not, looking at this this other vertex that I immediately came from and saying that there is a cycle because I see a gray or a black vertex in my neighborhood. Right? So excluding that one immediately that you came from, then yeah, you should continue here. Like, well, what if I went here, here, and here, right? So I'm seeing gray, 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 whatever, right? Now I see that gray vertex, but I didn't immediately come from it. There's a cycle. Okay. So you see a black vertex, you see a white vertex or a gray vertex in your in the neighborhood that you did not immediately come from, and that's immediately grounds for saying yes, you found a cycle. Right? And there are a whole bunch of other variations on this, right? Is there a cycle of length x, right? That one actually of length I don't know, L. There we go. L instead. Is there a cycle of length L? That actually is extremely hard, right? Because that gets into Hamiltonian paths. If you could answer that question, right? What is a Hamiltonian cycle? One that visits every vertex exactly once. If there are n vertices, answering the question of is there a cycle of length n, you're solving the Hamiltonian problem. You're solving an NP-complete problem. That's extremely difficult, right? So, might not be able to do this one. I don't ask you to do this one in your homework. Besides, you already did it on homework 1, right? You detected Hamiltonian paths or cycles, whichever one it was, right? But you did it in a brute force manner. You did it in an exponential algorithm. Yeah.
So we just have to find if there's a cycle. We don't have to find how long.
I forget what the handout says, but yeah, I think that there is or another variation would be, this is not in the handout, but another variation would be, is there a cycle, or given a particular vertex V, is there a cycle that involves V? Right. So that's a little bit of a variation. Let's think about that. Ideas. I want to know if this vertex is involved on a cycle or not, right? So, for example, this is kind of an uninteresting example because every vertex is involved on some cycle. But what if we had something else, like, say, I don't know, a bow tie. There. So this vertex is involved on a cycle right here. Right? Here, let me write one more thing. There we go. There. Because this vertex, all of these vertices were involved on some cycle. Right? But what about this vertex? Nope. It's not involved on any cycle. Right? So how could you detect that? Start from it. Okay, I like that. And then do what? If you ever come back to it. So do a BFS starting from there, right? And if you ever come back to it, then that was a cycle. If you never come back to it and you explore the rest of the graph here, right? However you're going to do it, right? Then no, there was no cycle involved on it. Right? You never came back to it. That's a good idea. Various other variations, like what if I gave you 3 vertices instead? And I wanted to know, is there a cycle involving all 3 of these vertices, right? Et cetera, et cetera. And some of those variations are really subtle differences. They immediately become extremely hard. In other words, there's only exponential algorithms known for them because they are NP complete. Right? So just one small tweak in each one of these questions can have completely different results in their complexity. Yeah.
So by a cycle of length L, do you mean find the cycle of length?
Well, find a cycle or give me a cycle, right? Remember, this gets into preview of what we'll do next time as an aside here, right? Types of problems, right? You can have what are called decision problems. Right? This is yes or no questions. So the question there would be, does there exist a cycle of length 5 or length L, right? You can have functional problems, right? Output a solution if one exists, right? You can have optimization problems. Output the best solution among all that exist, right? You can have counting problems. How many valid solutions exist? And can you translate the answer to one of these problems from one of these problems to another problem? In other words, can you take a solution for one of them and use that as a solution, adapt it, tweak it a little bit, and use it as a solution for the other version of the problem? If you can, that's called a reduction, right? And that gets into complexity theory. Right? One last question I'll leave you with is bipartite testing. Right? So one application of DFS/BFS would be detecting whether or not a graph is bipartite. So what is a bipartite graph? Let's get rid of that. A bipartite graph is where you can partition it into a left and a right vertex set so that edges only connect between the partitions. Something like this. I don't know. There we go. That's good. Right. That's a bipartite graph. You do not have edges of the form where it connects one vertex in L with another vertex in L. Right? All of these would be, nope, that's not bipartite. Okay? Can you partition the vertices into 2 partitions, disjoint partitions, so that edges only go across those partitions and not among the partitions? Right. This is a bipartite graph. Okay? What about, let's look at another common graph here. A complete graph on 4 vertices, a K4. Is it bipartite or not? Can I separate it out into 2 partitions? Well, let's try it. A, B, C, and D. So I'll start out here with L being A. I'll put A into L. Now A is connected to B, C, and D, so where would I have to put those necessarily? And the other one, B, C, and D. Ah, okay. I'm sunk here, right? Why? Because they're all connected. That's okay, but then these are all connected too, right? And that's not bipartite. Okay, fine. Let's look at another one. This is a C4, a cycle graph of length 4. Now, can I do the same thing? I'll go ahead and put A, B, C, and D. Now, if I put A over here in the left partition, then its neighbors, B and C, necessarily need to go over here in the right partition. Okay. There's my connection to these 2. There we go. Now, where would I have to put D? Well, D is connected to C, so it can't be in the right partition because C is already there. So it has to go over here. There we go. Writing the rest of my edges here. Was I successful in demonstrating that this is a bipartite graph? Yep. So instead of calling this L and R, call this gold and blue. There we go. Or square and circle, square and oval, whatever. Right? And let's go ahead and color those vertices, those colors. A and B, or A and D, and B and C. Now observe the relationship between each one of these. If you have a gold vertex here, all of its neighbors have to be blue. If you have a blue vertex, all of its neighbors have to be gold. Let me write one more graph here, a C5. That's going to be a cycle graph on 5 vertices. Let's try the same trick. I'll start at an arbitrary vertex and color it gold. I have to color its neighbors blue. The blue ones, I have to color its neighbors gold. What do we have in this case? We have gold connecting to gold. What can you say about this then? It's not bipartite. This is bipartite. So what do you think a necessary and sufficient condition is? We won't prove it today. We don't have time. But what is a necessary and sufficient condition for a graph to be bipartite? It can have even edges, even cycles, excuse me. You're right. It just can't have odd length cycles. Why? Because if you have an odd length cycle, you start at a vertex 1, 2, 3, 4, 5 means that you would have to end up back at the same vertex over here, and it can't be in 2 partitions at once. Right? So you can have 1, 2, 3, 4, right? You just can't have odd length cycles. Likewise, if you had a K3 or a C3, excuse me, right? Color it gold, and necessarily you have blue, blue. Right? Why? Because you alternate gold, blue, gold, blue, gold, blue, gold, blue, and that sinks you. So over the weekend, think about how you can use DFS or BFS to color the vertices and determine whether or not there are any odd length cycles, and then you can answer the question of whether or not it's bipartite. All right? Nothing due today, right? Yeah. It's all due next week. So have a good weekend.